Ready. So what we're about to move into, and you touched on it in the very last exercise, in the last chapter, is we're about to learn how to find the area under a curve. Okay, so area and the definite integral. So what they're saying here, just say this is the curve fx, and just say between A and B, okay, that blue section there is the area under the curve. Now, what they learnt that if I took little, okay, these are almost like rectangles, aren't they? Yeah. Okay, so what they found, how they sort of came to this was they realised that the smaller I make those rectangles, the more closer to the exact area that it'll actually become. Okay, so, and what they said, well, okay, if this is x, then this would be x plus change in x, or that's what they mean by that. Just means that little distance there is a small amount that you're adding onto the original x. Okay, it's just a next step over. That's all they mean by there. So the more subdivisions that we take, the more accurate the area becomes. So what they found that the area, so if this is the sum of, okay, each of those little rectangles. So imagine these rectangles. This distance is change in x, okay, and this one is fx. So if this, the width of all those rectangles is the same amount, then if we add up all these rectangles, okay, that's what they mean by the sum of. And this is your width and this is your height. Okay, so as with the limiting sum, so what we need to do, what that means is that distance there gets thinner and thinner. So what they actually do is they say, well, this is how we're going to write it. It's an integration symbol, okay? And this is how we actually say it. This is called a definite integral because it has parameters.
Literally this morning,
Yeah. So this is definite because it has parameters. These are what we call parameters. So what it's saying is that if I've got a curve, I'll just go over here, okay, just say I've got the parabola, okay, and if I said, all right, I want to find the definite integral of x squared dx, what this means is there's my curve y equals x squared, and I want to find it between 1 and 3. 1, 3. This is what you're actually finding. You're actually finding the area under the curve to the x-axis, okay, between 1 and 3. Okay, and yeah, so and we're about to go in to learn all different techniques. So integrating is the reverse of differentiating.
I thought that was the primitive.
It is the primitive, yeah. So what I mean by that, just say I've got this curve here, y equals x squared, then, and dy dx, okay, is 2x. So here I've differentiated, I've gone down. So if they give me the derivative, okay, I'm going up, and that's when you're integrating. All right? So what this is saying is that, just say if I have to integrate 2x, all right, that will go to the original function, which is the primitive, okay, which is x squared. But because there's no parameters, we have to add a constant, and I'll explain why in a moment. Okay, so differentiating, you go down, integrating, you go up, and that'll make more sense in a little moment. All right, so here is an example that they give you. So what this is saying, imagine I drew the curve y equals the absolute value of x, which is this curve here. Okay, it's the V shape, absolute value. It's saying what is the area between -2 and 2. All right, so you could do this doing just, that's a triangle, so that's got a height, this triangle here, I've got 2 of them, okay, and the base here is 2, the height is 2, so that's where this becomes 2 times a half times 2 by 2, okay, which happens to be 4. So that's an example of calculating that without knowing how to integrate. But you're going to learn techniques. But you could do that from a picture.
Yeah. Why don't we just stick to that?
Yeah. Yeah, I wish. But as long as you understand that a definite integral, so basically be a some function. So what this means is that integrate with respect to x. It doesn't always be x. It can be p's or t's or whatever. But if it was a t, then that'd be a t, that'd be a t. Yeah. Okay? A bit like when you differentiate. So this is an example of when you think about, I've got graphs A and B. Okay, I think this is graph A and this is graph B. Below, represent the function y equals fx. So this is y equals fx. Okay, and this one is gx. Okay, so this is velocity versus time. So this, so you think about velocity is distance over time, isn't it? Okay, so if I find the velocity times the time, that'll be the distance. Okay, so what they're saying here, this is the velocity versus time, even though they're using a y and an x-axis. So this is really like saying the area under the curve is equal to the distance. Okay, so
We know this.
yeah. So if we have a look here, it says when finding the integral, we are finding the area under the curve. So if we look at use graph A to evaluate the integral of the fx, so that means this graph, between 0 and 10, they want you to be able to calculate that area. Okay, how would you do that?
Split it up into 3 triangles, or 2 triangles and a rectangle.
Yep, so you're saying whereabouts? So let me just rub this off so I can see that properly. Okay, so what are you going to do? So we've got
A right triangle on the from 3 to what is that?
2.5, 3. Yep, 3 to 3. So you got that one there.
And you got the other one on the other side.
Yep, which is
10,
there.
and then you have that rectangle going down the middle.
Yep. So you've got this rectangle. So we've got that one, and then we've got that rectangle.
Sure, yeah. And then
Yep.
you have 2 more rectangles.
And then you've got 2 more rectangles, one here.
You could make that 3 smaller so that the bottom is just 1.
You could, oh, yeah. All right. Okay, so you've got 1, 2, 3, 4, and 5. Okay, so I'm going to tell you that the answer is 68.5. Okay, so how are we going? We could sort of go like this. We've got the area under the curve between 0 and 10 of the fx is like saying area 1, because I've drawn it on the picture, plus area 2, plus area 3, plus area 4, plus area 5.
But we're not going to do it like that, are we?
Oh, you can.
Yeah, but that's like time consuming.
Well, they've written the words out. Trapezium plus rectangle plus triangle plus, I find that one a little bit.
More time consuming. But yeah, isn't that what the whole point of this is?
Oh, no, yeah, no. You need to know how to do this, though. We're going to get to a point where you never have to do that.
Yeah.
But this is just helping with that understanding. And you do get multiple choice questions like this, where you may not be able to integrate the graph because you won't have the skills at this point in time to integrate all graphs. there'll only be a handful of graphs that you can. And when you go on to uni, you keep learning different techniques to integrate, more complex. So, yeah, fun. All right, so what do you reckon the area of 1 is?
One's the hardest.
One's the hardest. So what's each one? So that's like 1, 2, 3, 4, 5, 6. Do you reckon that's a 6? That height? So it's 9, take away 3, which is 6. And what's the base?
Yeah, it's 6.
Yeah, so that's going to be a half times 3 times 6. Would you agree with that?
Yep.
All right. What about area 2? That's a bit easier. So that's 2, 4, 5. So it's a half, and what's the base? 1, 2, 3, 4, 5. A half times 5 times 5. Would you say that's area 2? Yeah, and area 3's all right. That's just, what's that? 2 times 9?
Yeah.
Okay, what about area 4?
3
135
times 3.
Yep, 3 times 3. I agree with that. And what about area 5? 5 times 4. All right, go and put that into your calculator. Let's, fingers crossed. Let's have a look at example number 2. We want to find, this is the area under the curve, GX, between 0 and 3, with respect to X. That's what DX means. What kind of a shape is this?
A quarter of a circle.
A quarter of a circle. So what is the formula for the area of a circle?
2 pi squared?
No.
2
Pi r squared.
yeah.
Okay, yeah. So this becomes a half times pi. And what's the radius?
3.
It is 3, so it's 3 squared. So that's like saying a half times pi times 9, which is the same as 9 pi over 2. This is the exact answer, hey?
Why is it a half?
Because that's a quarter, sorry. Quarter. Good pickup. 9 pi over 4. Now, if they say to you, leave it as exact, leave it. If they don't say it, leave it as exact, because that's the easiest way. You know it's exactly that, because that'll be an irrational number. So you're better off giving the exact answer. Now, do I put units or units squared?
Units squared.
Yay! All right, so let's have a look now. Is the diagram to the right illustrates how the integral 25 minus x squared. So what does that graph look like?
A parabola.
Upside down, and where does it cut through the y-axis?
25.
So that's why that's 25. And it goes through 5. So it's like an upside down, but it's between 0 and 4. Okay, so what they're saying, the diagram to the right illustrates how the interval can easily be trapped between 2 rectangles. So the rectangles that they're talking about is this rectangle, okay, and this rectangle. So what they mean by trapped, okay, it means that the value of that area under the parabola is going to be between that rectangle and the big rectangle. Okay.
Going to be between it.
Well, yeah, the value of whatever this area is, that will have a value.
Yeah.
Okay. And whatever that value is, it will be lie in between that value.
Oh, and the
Yeah.
total.
And that value.
Yeah, okay.
And now I've completely demolished my diagram. Okay, so that's what they mean by that. All right, so what they've said here, they've said, okay, so the lower rectangle is OA, BC. I would have gone OA, I would have called that B, but anyway, because I like to do it in order. Or the outer rectangle, which is the bigger one. Okay. Evaluate the bounds, the upper and lower on that integral, that area. So what is the lower? How do you reckon the lower one is? The green.
From O to B and
Yeah.
from A to C.
Lower area. What are the letters that they say? O, A, B, C. What's that area?
4 times 9.
4 times 9, because it says here, whoops, I rubbed it out. See that 9 there?
Yeah.
Okay, so that's 4 times 9, which is 36. Now, what about the upper area?
Times
20, yeah.
Okay, so it's going to be 4 times 25, which is 100. Okay, so what they're saying is that that value, whatever that works out to be, has to lie between what?
36 and 100.
Yeah.
And we using mathematics language, we put 2 less than signs. So it's going to be some number between 36 and 100.
Oh,
So I'll give you some time to get that one down.
how do you know if it's going to be, like, is it always lesser than and there's no such thing as equal to? Well, obviously not.
No.
Don't worry, that's a
Yeah.
dumb question.
That's all right.
I always want to put brackets around B of X every time.
Okay. This is a really funky bit.
Oh, great.
Okay.
I'm not sure I understand.
No, you wouldn't. You don't know, you're not very good at maths, Siri.
Bit of a weird thing to say to a computer program.
Yeah, that's true. All right. Okay, so let's have a look at what they mean by this one. So they're saying, use that same question. Here's your parabola between 0 and 4. It says subdivide that between here and here into 4 subintervals. 1,
Oh, okay.
2, 3, 4. Okay. So what they're saying is that we're going to find the area of that rectangle. Then we're going to find the area of that rectangle. Find the area of that rectangle. Okay, and then the next one, there's nowhere to go. Okay. So, well, let's have a look here. So we'll call those the upper rectangles, but the lower rectangles, okay, are going to be these ones. All right. So go from the lower point. Sorry, we've got one more here. Sorry. That was a red one. There. Oh, you know why I've got it so wrong? Sorry, I was looking at why haven't I got enough rectangles there because of that 4. Sorry.
Oh, no, okay. Yeah, no, you're fine.
Yeah.
You're fine.
Sorry, I'm sincerely sorry about that. Sincerely sorry. All right, because that parabola,
Integration provides insight.
so that's 5 there, isn't it?
Sure.
Yeah, because 25 minus x squared is like saying 5 minus x, 5 plus x.
So there should be another rectangle.
Yeah. But we only want the area between 0 and 4. Okay, that's why I was a bit confused. And how many subintervals did we have in that area?
4.
4. So split it in half, split it again. That is better. All right. So what we're going to do now, it says subdivide into 4 intervals to tighten the bounds further. So we want to have this like what we've got above, but we want to change our numbers because we've got the sum of those 4 rectangles in the lower ones and the sum of the 4 upper rectangles. So we've got to find out what those numbers are. So let's have a look at the area of the 4 lower rectangles. So this is here. So I'll do it in green. Okay, so what would be this x value here?
1.
1, 2, 3, 4. So if I put 1 in, because that'll give me the height. So if fx equals 25 minus x squared, so if I put 1 in, what will that be? What will the height of that be? Put 1 in to the graph, minus 1 squared.
24.
So that'll be 24. So this little lower rectangle would be, so let's just put area of 4 lower rectangles, area of 4 lower rectangles. So that's going to be, the first one is going to be 1 times 24 plus, now what's the next one number by? So if I put that in, where's that? What's that value here?
It's going to be 25 minus 2 squared.
Yep, which is 25 minus 4, which is 21. So that's going to be plus 1 times 21. They're all going to be 1 times because they've all got a width of 1.
Yeah.
Okay, now what about the next value here?
25 minus 9.
3 squared, which is 25 minus 9, which is 16. Okay, and then the next one will be 25 minus 16, which is 25 minus 16, which is 9. 1 times 9. So really what I'm doing is I'm going 24 plus 27 plus 16 plus 9. Okay, and when you add that up, you get 70. So that's going to be the number that's here. This area is going to be between 70, and now we're going to find out what this number is.
Okay.
All right, so the upper rectangle, area of upper rectangles. Okay, same deal. They're all going to be 1 times something. See if you can think what the number is for the first one.
1.
1 times, so that's 1, but the upper rectangle is this height. So what is that height? What's-
Oh, hang on. 25?
25, because that's where it cuts. Yeah, yeah. So that would be 1 times 25. Now let's look at this one. That's 24, isn't it?
So we don't use the formula for that one, for this one.
No, we're not. No, we're just doing all. Look at the question. It's saying divide it into 4 sub-intervals to tighten the bounds further. So what we're doing is finding the area of the bigger formula now. Okay, so we did use the formula because this time that height, okay, you put 1 into there because that's the height there. It's the higher one, which is F1.
What? Hang on.
You're right.
What you just said.
Hang on. All right, so here is my graph. That's 25. Okay, this is the graph fx equals 25 minus x squared. So I've got 1, 2, 3, 4. Okay, and to work the lower ones, you worked it out on this one.
Yeah.
But the upper ones are done, okay. What is, that's the height. So it's going to be F0, which is 25. So that's why it's 25. It's got a height of 25.
Yeah.
So the next one has a height of F1.
Okay.
Yeah, so you're using the left-hand one
Yeah.
for the upper one. So that's why it's 1 by 24. And then it becomes, and then this one is going to be, the third one is F2, which is 25 minus 2 squared, which is 21. And then the last one is F3, this one here, which would be 25 minus 9, which is 16. And when you do all that calculation, you get 86. All right, so what we've actually done is we've tightened up the boundaries. We've narrowed what the area is going to be. Up here, it was pretty loose. It was just saying, oh, the area is somewhere between 36 and 100.
Yeah.
Whereas this one, we're narrowing it down, the gap.
Yeah.
It's now between, so you imagine if I had 100, it'd be that close.
Yeah.
Yeah, and that's what calculus is, integration is.
Is that 21? Because if you put that f of 2 into the...
F2 is 25 minus 2 squared, which is 24. But that last one was F3. That's F3.
Yeah, which is 25
Yeah.
minus 9.
Yeah, which is 16.
Oh, yeah. Hang
Yeah,
on,
that's the
I've
last
done a
one.
little Doobie here.
Yeah.
It's alright.